This next video will introduce section 3.4, which discusses limits as x approaches the infinities. This is a situation where, especially after finishing section 3.3, which had loads of information, this is one nice topic. And we've kind of already done this at the very, very beginning of the class. This was formally where it will come up when we think about when we have functions and what are the techniques to evaluate those limits, but we kind of already have the idea if we look at the graph. We did a little bit of this way back at the beginning of class, so let's kind of just remind ourselves a little bit. So if this was my function f of x, and if I asked you, what is the limit of f of x as x approaches minus infinity? What is the limit of f of x as x approaches positive infinity? All this is really asking is what is the extreme end behavior? Ignoring everything in the middle, notice I don't even have an x-axis labeled anymore. So just purely looking, as x goes to negative infinity, what is the extreme left side behavior? Well, in this graph, as x keeps going further left, that would approach negative infinity. The y values keep going down lower and lower. So as x approaches negative infinity, so does y. If this graph did something like this on this far side, then as x approaches negative infinity, the y would approach positive infinity. So that's certainly a possibility. A lot of our graphs have this shooting up or shooting down in that sense, not at an individual vertical asymptote, but just that extreme end behavior. I keep going down and to the left. I keep going up and to the left. Or as x approaches positive infinity, what happens on the right side? So that is certainly one possibility. Another one, this is not because it's x approaches positive infinity, it's just trying to point out another possible situation here. But in this one, as x approaches positive infinity, look at what's happening here. This isn't continuing to go up as x keeps going further to the right. What I try to show here is this completely flattened out. When we have these situations, we normally would have like a little bit of a dashed line to try to indicate that I'm approaching that dashed line without touching it. And we've seen that before. That's similar to a vertical asymptote, but it's a horizontal dashed line, and that goes with the idea of a horizontal asymptote. But where is that horizontal asymptote? It's at a y value of 2, and that's what this function is doing. The further we go to the right, the closer the graph gets to this dashed line, the closer it's getting to that y value of 2. So that's something we have to realize here. When we take these limits, positive or negative infinity, the infinities are possibilities, but so are numbers, and those numbers, I shouldn't abbreviate, HA is giving me a horizontal asymptote. That's what I'm literally seeing in this particular situation. Very quickly, I don't want to try and establish those as the only 4 possibilities. So let's just do this. Let me just change the function. Let's make it g of x this time. And there's my function. So now let's take a look at the limit of g of x as x approaches positive infinity and as x approaches negative infinity. And this last situation, again, I don't have much labeled here, but you might recognize this. I was basically drawing a sine curve. And what's happening? Well, as we go to the extremes, we just keep getting this oscillation, right? When we go back to this first one, well, we're going down and left forever. We're going up and left forever, up and right forever, right and down forever. Are we flattening out a particular y value? Well, this is doing none of those things. This just keeps oscillating up to 1, down to -1, up to 1, down to -1 forever. So this would be a situation where this limit simply does not exist. And then there's no difference on the negative infinity side here. What's happening on the extreme left? The same thing. I'm not establishing an up left, a down left. I'm not establishing a flattening. I just keep doing that oscillation. So this would be another does not exist. The trig functions in particular are where these situations, the sine and cosines, they have that oscillation. So those are common examples where you'd see it does not exist. Okay, but now how is this supposed to help us when we're looking at an equation? And what we need to realize here is that infinity and minus infinity are basically a special case. Infinity is not really a number. When we're looking at the graph, we can try and treat it like our other limit problems. The idea of approaching, realize you can't approach minus infinity from the left and the right. Negative infinity is already as far left as you can go. You can't get further left to then approach it from this side. Similar with positive infinity. You can't approach positive infinity from the right. You could only approach from the left. So there's a few technical differences, but the basic understanding of limits and what you approach, that still works in the graphing picture, in the graphing situation. But when we have the equation, we need to take this a little further. So let's take a look at a very, very simple idea for a moment. Let's take a look at the limit as x approaches infinity, and let's look at x cubed minus 2x minus 4. Nothing too fancy going on here, a very basic function. And let's still go back to that initial idea of limits and what we approach, and let's go back to that whole xy table situation. Let's pick some x's that approach this and see what's happening to the y's. So, if I let x approach positive infinity, I'm talking about going right forever, I'll start off letting x be 10. It's really not making much of a dent approaching infinity, but it's at least getting us to the far right side of our graph. And when I plug that in, literally 10 cubed is 1,000, minus 2 times 10 is minus 20, minus 4. I'm not going to do the rest of the arithmetic. I'm just going to keep going to then establish my point. So now let's keep letting x get closer and closer to infinity. So I'll let x be 100, and then we'll let x be 1,000. 1,000 still barely scratches the surface as far as letting x approach infinity, but it'll make my point that I'm about to establish. 100 cubed would be 1,000,000 minus 2 times 100 minus 200 minus 4. 1,000 cubed would be 1,000,000,000 minus 2,000 minus 4. The point of this exercise is that when x gets really, really big and similarly really, really small, the idea of approaching positive or negative infinity, look at the actual numerical values and realize that these later terms are basically irrelevant. If you have $1 billion and then lose 2,000 and then lose $4, to significant figures, you still have $1 billion. And that's only letting x go to 1,000. Imagine what would happen if x is 10,000, 100,000, 1,000,000. It just gets worse and worse. These other terms are essentially irrelevant. So this is, again, a very special case. When x is approaching the infinities, we could basically focus, this is an informal term, I call it, we could focus on the dominant term. So that doing this limit problem, I really don't have to care about these at all. I'd establish the dominant term, which is the highest powered x, the highest power of x in the problem, and I could ignore everything else. So by ignoring anything else, now this is basically just a plug-in, but we still need the idea of infinity. Let x be a big positive number, you cube it, and your y is an even bigger positive number. So as x approaches infinity, this function approaches infinity. Similarly, if I did that same function, x cubed minus 2x minus 4, and now I let x approach minus infinity, I'd still get to ignore these terms, and I could just focus on the x cubed, but now I have a huge negative number. A huge negative number cubed is still a huge negative number, so I would get negative infinity. Little things here, everyone, to realize. Even if this was multiplied by, say, 1/2, or x cubed divided by 10, you cube a huge number and divide by 10, you still have a huge number. We still get a lot of infinities floating around here, so a lot of this has to do with the sign. But as I keep going here, let's do another problem. Let's evaluate, let's formalize these directions, evaluate the limits, and let's take a look at this next one. I'll call this problem number 1. The limit of x cubed minus 6x divided by x to the 4th plus x squared plus 10. Let's take that limit as x approaches infinity. I'm still a big fan of, again, what I call the dominant term. But what we'll do here, the only subtle difference is that now I'll establish the dominant term for both the top and the bottom, for the numerator and for the denominator. But after I get that dominant term, I'll still get to get rid of a lot of the extra terms, and that'll allow me to do more work. So what am I saying here? Well, in the numerator, the x cubed is the dominant term. In the denominator, the x to the 4th is the dominant term. So I get to still keep my limit notation here. I'm not able to plug in. There's still that idea of plug in. And there's too much going on to plug in right now. But by establishing the dominant term, I get to ignore everything else. So now I've got an x cubed over an x to the 4th. So without all those extra terms by addition subtraction, that allows me to clean this up algebraically. That this becomes 1 over x. And now that there's only one variable left, now I could think about plugging in this huge number. So I plug in a huge number, 1 over 100, 1 over 1,000, 1 over 1,000,000, 1 over 10 million, and I'm getting closer and closer to 0. I'm just getting smaller and smaller fractions, 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000. That is approaching 0. This doesn't always happen, but this would be the same thing even if x approached minus infinity. Positive or negative infinity, I get to focus on dominant terms. But now even though it's going to negative infinity, I'd get 1 over negative 1,000, 1 over negative 10,000, 1 over negative 1,000,000. It would still be approaching 0. So that would be my limit. And if I was actually going to get to the graphing part, again, 3.5, we're going to put all the ideas of increasing, decreasing, concave up, concave down, and these limits, these extreme end limits are formally called our end behavior. So if this was our original function, this would have end behavior of 0. This would have a horizontal asymptote, y equals 0. That's just interpreting what this is telling us. You don't have to put that note here. Just evaluate the limit, the answer is 0, but I want to reconnect with what we were saying up here. If we get these limits are infinities, that's not a horizontal asymptote, but if we get a nice number at the end here, that is a horizontal asymptote. Before I do another problem, I just want to point out a subtle difference between what I'm doing versus what the book does. If the book does this problem, they talk about not finding dominant term of top and bottom, just finding the dominant term of the whole function, divide by that power of x. So in the book, they divide everything by x to the 4th in this problem. So they would have the limit. Let's just go back to x approaches positive infinity. X cubed over x to the 4th is 1 over x, minus 6x over x to the 4th is 6 over x cubed. X to the 4th over x to the 4th is 1. X squared over x to the 4th is 1 over x squared. 10 over x to the 4th is 10 over x to the 4th. And now they'd expect you to realize this goes to 0. This goes to 0. This goes to 0. This goes to 0. So you've got 0 minus 0 over 1 plus 0 equals 0 over 1. Same 0 that we had a moment ago. Not a bad technique. I just prefer this way. This will always work just as well as this, and typically just leads to a lot more of a simplified problem to look at. So for the next few examples that I do, I'll be sticking with the dominant term approach. I don't mind at all if you prefer this way. I just think, again, most students in my experience do a little better with this. So let's keep going. We're still evaluating the limits. And now let's take a look. The limit as x approaches infinity. And this time, let's look at x squared minus 10x to the fourth all over 5x to the fourth plus x cubed minus 1. X is approaching infinity. That is such a crucial piece, everybody. The one big problem that comes up in this section is that people try applying this dominant term idea to all limit problems. You got to remember, if I asked as x approaches 1, you're plugging in 1. If you're only approaching a number like 1 or -2 or 5, any regular number, those extra terms make a big difference. It's only as x approaches plus or minus infinity that we get away with this dominant term trick. Okay, because that's what we're up to. Now dominant term, still not taking my limit yet. First simplifying, so I'm only looking at minus 10x to the fourth from the top. The minus is a part. It's not just the power of x. It's the whole term, coefficient and sign included. I try to just be a little tricky here, right? Oftentimes, our polynomials start with the highest power of x, but this was just slightly out of order. So just to realize, right, it's just the highest power of x. In the bottom, that's that more traditional, the 5x to the fourth is the first term, and that does coincide. But now in this one, the previous one we had x's cancel, but we still had x's left. In this one, the x's cancel entirely. There's no x's left. And we're still using limit properties. If there's no x left, the limit of a constant is that constant. So this limit equals -10/5, which we can reduce to -2. That would have been identical if it was x approaching minus infinity. We'd still have the dominant terms. The powers of x would cancel entirely. Again, this would give us a horizontal asymptote y equals -2 now. We'd have that flat line that we'd approach on both sides of the graph for our end behavior. But just establishing the limit, that's it. So before I keep going, I just want to make one quick thing clear. I'm asking you to evaluate the limits, and I'm starting you off with this limit problem. But just a quick little alternative. If I said, does y equal x squared minus 10x to the fourth over 5x to the fourth plus x cubed minus 1, does this function have horizontal asymptotes? I would do this work. I would take both of these limits, and I would see if I get a nice numerical answer. So just to already start to connect the dot, try to get us a little more prepared for when we're making the sketches and we're trying to use this information. End behavior is about taking these limits. Whether you're specifically asked for a horizontal asymptote or you're just trying to find the end behavior for a function, you take the limit as x approaches the infinities. Okay, 2 more of these. And now let's go back to, again, we're just evaluating the limit. Let's focus on number 3. Now let's take the limit as x approaches positive infinity, and let's look at the square root of x to the fourth minus 6x plus 10, all divided by 4x minus 7. Still dominant terms. Still focusing, I've looked at here and here, but just be careful. The dominant term of the top is not x to the fourth. The dominant term of the top is the square root of x to the fourth. That square root still needs to be a part of that dominant term. The denominator, it's just the 4x. And even here, it's not just the ability to cancel off x's. Even here, now we have the ability to break down the square root further. The square root of x to the fourth is x squared. I couldn't do that when I had the minus 6x plus 10 there, but I can take advantage of that here. And this would simplify x squared over 4x to x over 4. Now I've got an x left. So what happens when I plug in that value? Huge positive value for x divided by 4 is still a huge positive value. So as x goes to positive infinity, this limit still goes to positive infinity. What about if I change the problem to negative infinity? Still an infinity, still dominant terms. But now I would be plugging in a huge negative value for x. So I get huge negative value divided by 4. And remember, still huge. I'm not talking about negative 10 divided by 4. I'm talking about negative 1,000 divided by 4 is negative 250. Negative 1,000,000 divided by 4 is negative 250,000. So even though I'm still dividing, my number's getting smaller, the bigger value I plug in, the bigger I still get an output. That would then be negative infinity this time. Last problem for this section. Numbers 1 through 3 really establish the big picture. For some of you, especially those from pre-calculus, maybe at QCC at an earlier semester or some similar class in high school, you can go back to problems like this and you knew things about degree, that the degree established these facts, that back in problem number 1, the higher degree in the denominator led to this horizontal asymptote, that they had same degree. I mean, there are other properties, but this is why those rules existed in those previous classes. Now we have a better ability, instead of just memorizing a chart, and those things only applied when you had rational functions, polynomials over polynomials, like this one, polynomials over polynomials. But for something like this, we didn't have anything, but with the limit ideas, we could still break these down and get answers. So again, just one more here. Number 4, let's take a look at the limit of, let's do 10x plus 1 over the square root of x squared plus 1. And like the ones we've been doing, we'll do both limits. I'll start off taking a look at the limit as x approaches positive infinity, then we'll do negative infinity. This, just a slight trick, everybody. If you've been really sharp and following, you'll notice back in problem 1, positive or negative infinity, we still got the same answer. That when we had a horizontal asymptote, it didn't matter if x approached positive or negative infinity, we got the same answer. And that also happened again up here in problem number 2. Here, we did not get a numerical answer, we got infinity, so now different things can happen. But so far, that's not a random thing that happens. That's a very common situation, but it doesn't have to. And this is the example that shows we don't always get the same thing, even if we get one of these nicer numerical answers. But it feels like it initially. I look at dominant terms. Let's start off focusing on x approaching positive infinity. And I get 10x over the square root of x squared. Here's the issue, everybody. Just like here, the square root of x to the 4th is x squared, people do something similar. They go, oh, the square root of x squared is x, 10x over x cancels, so I just get 10, and we're done. And then they do as x approaches negative infinity, and they get the same thing. Here's the issue, everybody. This can't be negative. You had a square root, so what's underneath it can only be positive, and after you take the square root, there is no plus or minus, you'd only get a positive answer. Technically, the square root of x squared is the absolute value of x. So now, if x's are positive values, then this does work perfectly, that I can get 10x over x cancels and I just get 10. But as x approaches negative infinity, I have to think of this as a negative x. I'm plugging negative values in. This will be negative, but this will come out positive. So it's really 10x over negative x, and the answer would be negative 10. This is a rare function that would have two horizontal asymptotes. On the right side of the graph, we'd have something approaching this part up here, but on the left side of the graph, we'd be approaching this line. Again, everybody, that's rare. I want to point it out. The book does an example to point that out as well, so we're aware that could happen, but these are the types of problems that I expect you to be able to handle.